So Maxwell equation would be the starting point. So you don't have to worry about the derivation of that. So that is not required. But at least you should have studied what is meant by Maxwell's equation in vacuum. So that is the starting point. So what are these Maxwell's equation? Let me write down for clarity. First one is the Coulomb's law, divergence of E equal to rho by epsilon naught. The second one is the divergence of magnetic field is 0. So that is 1 and 2 we are not worrying about, but this is how we write down. The next one would be the Faraday's law given by del cross E equal to minus dou B by dou T. And finally we have the Ampere's law, del cross B equal to mu naught into current density J. Then plus you have mu 0 epsilon 0 into dou E by dou T. Equation number is not very important. So let me therefore write down 1, 2, 3, 4. So which one is equation number 1, which one is equation number 2? So there is no uniformly we need not maintain, but let me just write down 1, 2, 3, 4 for referencing purpose. So here I would like to first of all emphasize the point that these equations are valid in vacuum. Okay, which means that the zeros that are there in this equation, that means these zeros, mu 0, epsilon 0, etc., they will remind you means they will enable to identify that these equations are generally valid for vacuum. So that is the meaning of the 0 there. So the starting point is this is the starting point. So that is the point to be noted. Now let me therefore refresh your memory that the first equation is basically the Coulomb's law. The Biot-Savart law that we are going to have will be the equation number 2. So these are written in the divergence form or in the differential form. And then the Faraday's law is written down in this particular fashion, namely curl of electric field. And the Ampere's law is written like this. Coulomb's law and Ampere law, you can see several years gap. So similarly, Ampere's law, there will be a lot of time gap will be there between the Coulomb's law and the Ampere's law. So these things are scattered over time. So Maxwell has brought everything together under one head or one roof and under the vector calculus, in the sense that you are performing the differential operators on the electric and magnetic fields. So what is the purpose of doing this? The primary reason why Maxwell has written down this equation in this particular form is that the moment you say that electric field and magnetic fields are vector quantities, then it has to obey the mathematical rules of vector calculus. That is the point to be noted. Okay, so it can be a physical object, that's fine. Electric field and magnetic field can be a physical quantity, that is okay. But the moment you say that the electrical field and magnetic fields are vector quantities, indirectly, or we say that these fields or these quantities should obey the mathematical rules, whatever be the case. So you have several rules in vector calculus. Those rules have to be obeyed. That is a point to be noted. To start with, what we will do is, we will first of all try to establish this equation. Establishing means proving this equation, starting from the corresponding experimental observation. So what is our next interest is that we would like to solve these equations. The right hand side is not 0 in equation number 1. For example, this one doesn't have the 0 on the right hand side, and whereas this one is having a 0. So what is the meaning is that the moment you don't have 0 on the right hand side, then we say that equation number 1 is inhomogeneous. That's the meaning. So equation number 1 is inhomogeneous partial differential equation, and this being a 0 here, we say that this is homogeneous differential equation. So these two things are clear. So which is inhomogeneous, which is homogeneous? The equation number 1 is inhomogeneous because right side is not 0. Equation number 2 is homogeneous because right side is 0. So that's clear. Now come to the equation number 3. For equation number 3, what you have to do is, you can take this to the left side, because magnetic field and electric field are, they are the field, right? All the field you have to keep it on the left hand side. That is the idea. So take this to the left hand side. Then if you take to the left hand side, then right hand side is 0. So I'll read it: del cross E plus dou B by dou T equal to 0. So therefore what happens is the right hand side will be 0. Therefore equation number 3 is also homogeneous differential equation. That's clear. Now come to equation number 4. Now equation number 4, again you have to do the electric and magnetic field, you have to take it to the left side. Magnetic field is already to the left side, right? So you take this term to the left side like this. So once you take this fellow will become minus here. That's why. And what is remaining on the right hand side is mu naught into J. And J is the current density which you are going to apply. So that is called source. If you are going to apply the current, if you are going to supply the current, they are known as the source terms. Therefore, mu naught into J is the source term, and that has to stay on the right hand side. You can't take that also to the left side. Okay, you can always ask the question, take everything to the left side and put a 0 on the right hand side. That is not the idea. The idea is electric field and magnetic field, that they have to stay in the left hand side. Anything other than electric and magnetic field, that has to stay on the right hand side. That is a rule. Okay, so if you do like that, then mu naught into J will be staying on the right hand side. Therefore, as long as there is a current and current density present in the system, then the right hand side is not equal to 0, and therefore equation number 4 is inhomogeneous differential equation. So now it is clear, right? How many homogeneous equations are there? How many inhomogeneous equations are there? So that is clear that equation number 1 is inhomogeneous, equation number 4 is inhomogeneous, whereas equation number 2 and equation number 3, they are homogeneous differential equations. So the divergence of B is always valid. So that is what I am trying to say, irrespective of whether it is vacuum or not. Okay, now what is to be studied now? Okay, so let me explain this, what I have written till now. The meaning is that either you say that we are going to solve the solution of Maxwell equation, okay, or you are trying to get the Maxwell equation solution under static condition. What do you mean by static condition is that the time derivatives you will have to keep 0. So you should not allow the magnetic field to vary. So this fellow will go to 0. Similarly, don't allow the electric field to vary. So this fellow will go to 0. So therefore, some of the terms will go to 0, or the time derivatives will disappear. And in that particular case, we say that the Maxwell's equations correspond to static condition. Static condition means what you call the fixed value of the electric field and fixed value of magnetic field. You are not allowing to vary that. That is the meaning. So under such situations, it will be easy to solve to begin with, because this is how you start with, right? So you don't want to complicate the situation. So make the static condition and then try to solve it. That is a simple meaning. But technically, there is another name for that. What is the meaning of this solution of differential equation is that it is mathematically known as boundary value problem. Because mathematicians prefer to use certain technical term rather than simply always telling solving equation. Okay, so the equations are known as the boundary value problem. The reason why it is called a boundary value problem is that you are going to solve this particular problem over certain region of space. That is called boundary. Boundary means we are talking about space. You are not going to solve it from minus infinity to plus infinity. That much solution you can't get it. Okay, so you have to. I am trying to explain why do you use the word boundary. Boundary means if you are going to use certain region, then that particular region will come to an end. Okay, if you are sitting in a room, that room will come to an end, right? If you open the door, you will go outside. So you say that the 4 walls of the room is your boundary. That is only called room. If you come outside, you are not inside room, right? So you can now understand what is boundary. So boundary value problem means that on these boundaries, that means on the 4 sides of the whatever that we are going to discuss, you will have to provide the value of the electric field and magnetic field as boundary conditions. So that is why these problems are known as boundary value problems. In electrostatics and magnetostatics, what I mean to say is that in electrostatics means in equation number 1. So if you are going to solve equation number 1, okay, together with equation number 3, because 1 and 3 corresponds to electric field. If you are going to solve together 1 and 3, then it is known as electrostatic boundary value problem. That is the meaning. Then come to the second one. If you are going to solve 2 with 4, the equation number 2 with the equation number 4, if you are going to make a solution to that kind of combination, then we say that we are studying the magnetostatic boundary value problem. So that is a technical term. So whenever you use a technical term, you should know what we are doing actually. That is why I am trying to explain. So you can now understand what is the meaning. If you solve equation number 1 and 3, it is known as electrostatic boundary value problem. If you solve equation 2 along with 4, then it is known as magnetostatic boundary value problem. This is the technical mathematical terminology for this. Now the question comes now, why should I solve equation 1 with 3? Why do you want to combine with? You can solve equation 1 alone. So this point you have to be careful. Can you solve equation 1 alone, or that you have to solve 1 with 3? So this is something interesting here. Now the point is that ultimately the important point is that you can't solve equation 1 alone. So this is very important. So that comes basically from the rules of the vector calculus. Okay. So right now you don't have to enter into the detail, but the point to be noted is that you can't solve only the equation for divergence alone. That is not at all possible, because it is incomplete. Divergence alone will be incomplete. In order to make it complete, what is required is you have to specify the curl also. Okay, so you see carefully that there is an electric field here, there is an electric field here. Now what is 1 and 3? What is 1 and 3 is going to tell you is, equation number 1 will give you half of the information about the electric field. Only half of the information. It will not give you the entire information. Then where will you go for the remaining information is, you have to go to equation number 3. Equation number 3 will give you the remaining information that was not available from 1. That is important. Okay, so if you combine the information from 1 and 3, then you will be getting a complete knowledge about the electric field. So this is the point to be noted. This is purely mathematical in nature. There is nothing to do with physics here. This is quite important, and this is where the knowledge of vector calculus is required. Okay, so generally vector calculus is already studied in your BSc. Whether you are given importance and you read it, or you just memorized some formula and passed the course, so that those things are different. But now the point to be noted is that the knowledge of the vector calculus is very important. Okay, so memorizing some formulas in vector calculus, it will not going to help you. So now you can understand what I am trying to explain. The divergence del dot will give you half of some partial information. That's what I mean to say. Okay, a part of the information will be available from the divergence specification, and the remaining knowledge about the particular vector, that means electric field vector, will be available from the curl specification. Curl means del cross. So specification means giving the value. Giving the value means equal to something, right? Equal to 0. Whether it is 0 or something else, whatever it is given to you, right? That is the point. It is equal to rho by epsilon, where rho is the charge density. So you already know what is the charge density. That is called a specification. So the specification of the divergence together with the specification of the curl will completely specify a given vector quantity, and the given vector quantity is the electric field. So therefore you have to solve equation number 1 together with equation number 3. It has to go togetherly. You can't solve independent of that. So this is the point to be noted. And the same explanation is now valid even for the case of 2 and 4. Now you understand why should you solve equation number 2 along with 4. The reason is equation 2 will give you only partial information about the magnetic field, namely the divergence, whereas the curl will give you the remaining information about the same magnetic field. So the point to be noted is that this magnetic field and this magnetic field are identically same magnetic field. That is the point. They are not different magnetic fields. Similarly, coming to the equation number 1 and equation number 3, the whatever electric field is there here, it is identically same electric field here. That is the point to be noted. And therefore, equation number 1 will share partial information, and equation number 3 will share the remaining information. So that if you combine both of them, you will be getting a complete information about that particular field. That particular field means either electric field or magnetic field. So now you understand the meaning of this particular statement that I have written. Electrostatic boundary value problem means solving 1 with 3. Magnetostatic boundary value problem means solving 2 with 4. So that particular terminology is now clear, and therefore you now know what is that we are trying to do. So we are interested to solve the differential equations basically. That is the meaning. And once you finish this, then next what to do? So the next immediate question comes, why should you always talk about vacuum? Here you see vacuum is there. Okay, why should you always take vacuum? So that is the question comes. The answer is yes, you can always go away from vacuum and then talk about material media. So I will therefore write down that. So once this idea is clear, next step will be that we are interested to study the influence of the material medium. Okay, influence of the material medium. What do you mean by material medium? Material mean any material. That's what any material is called material media. So by that we can understand something like dielectric. We can say that means electrical insulator, or that is one possibility. Second thing is you can consider conductors, and you can also consider magnetic materials. Okay, so these are the possibilities. So I'll write down magnetic materials. So you have three options: dielectrics, or a conductor, or it can be a magnetic material. So which means that now we are no longer talking about vacuum. You came out of the vacuum. So therefore this particular study is known as the boundary value problem. BVP means boundary value problem in presence of material media. So now you understand what is this. This is also boundary value problem, but now it is in presence of the material medium. What is the meaning? The meaning is, once again I'll write down for clarity, the meaning is Maxwell's equations in material medium. Okay, so I am writing this particular statement, Maxwell's equations in material media, because in the previous step, or in the beginning of the board, I have written down Maxwell equation in vacuum. So Maxwell equation in vacuum and Maxwell equation in material medium are not identically same. They are not identically same. There is some changes are there. That is why I am emphasizing this particular point. Okay, so let me therefore stop here before writing the next point. So the points are now clear, that the A and B. Okay, so which means that you are going to study the boundary value problem in vacuum, boundary value problem in the presence of material medium. These two things we are going to study. So now we are going to study the third one. Okay, the third one, the terminology will be slightly confusing. So, but however, there is no need to worry. But the point is that the third point which I am going to write down, I am trying to write down boundary conditions. Okay, this is not the same as the boundary value problem. So let me write, now I will write down. So you understand that point. So boundary conditions to be satisfied by the electric and magnetic fields. So this is the one which we are going to study afterwards. Okay. What are the so let me explain. What are the boundary conditions to be satisfied by the electric field and magnetic field? So this will be the second point. So I'll write down that first point is that, and second point is this. So as I explained, let me also write down for clarity that because the word boundary is coming everywhere, you may get a little bit of confusion. So to avoid that confusion, I will now write down a note. So please note down this note. So what is the point to be noted is that boundary value problem is not the same as boundary condition. So I will write down that. Okay. Boundary value problem is not the same as, I will write not equal to, that means it is not the same as boundary conditions to be satisfied. So what do you mean by this? Since in two places you have the boundary, you may get a confusion. So I would like to tell that boundary value problem is different, boundary condition is different. Boundary value problem means basically solution. Let me write down. This means solutions to differential equation. That's what I already explained. So the terminology is clear. Solution to differential equation. What is the differential equation here? Namely the Maxwell equation. So that is your left hand side, boundary value problem. But what is there on the right hand side is completely different. What is the boundary condition to be satisfied? That means what happens is boundary condition to be satisfied means when the electric field is making a transition. Let me stop here. Okay, I'll first explain and then move further. Okay, what is the meaning of the boundary condition to be satisfied? I would like to explain. So otherwise it may be a little confusing to you. So let me therefore explain here. Suppose if you have a vacuum here. Let me write down that you have a vacuum here. And then you have an electric field. Suppose you have an electric field in the vacuum. So this is fine. And the electric field will be there everywhere in the vacuum. Only one particular arrow I am drawing. If you go to another place here, a similar parallel line you can draw. And that is the meaning. The meaning of the parallel line is that, suppose if you draw several of the parallel lines like this, then we mean to say that the electric field is uniform. Okay, that's the meaning. You can draw several parallel lines. So that is clear. Now the electric field is present in vacuum and it is uniform. That much is clear. Now the point to be noted is like this. Suppose that I suddenly bring, I will now suddenly bring another medium. So what is the medium that I am going to bring is, you can bring any medium you like. Okay, so for example, I am going to bring some medium like this. So let me therefore draw, so that will be easy for you to visualize. So if I am going to bring another medium which is represented by some kind of a pink color like this, so then what happens? So this is your pink color material medium. Material medium means dielectric medium, insulator, electrical conductor. It can be anything. Okay, dielectric is also okay. Electrical conductor is also okay. Anything should be there. Magnetic material, anything. But it is not vacuum. You understand? This pink color is not vacuum. That is a point to be noted. This is not vacuum. So the question is this one: when it is coming and touching here, you're able to see, right? This particular electric field will come and touch here. Now once it touches, the question is this: will it continue to travel in the same straight line like this and then come out? That's the point. That is the question that we are asking. So the question is, will it also travel the same straight line? That means, can I simply extend the white color line into pink color line? That is what is the question. The answer is no. So let me therefore erase. Okay, this one I will erase. So it will not travel like that. That means you cannot extend the pink color line like this. So that is a point to be noted. So the conclusion is that either it will be slightly deviating like this. So now you can see that the white color vector and the pink color vector is slightly changed. So this will be the electric field vector inside the dielectric medium. So you understand that because of the material medium, what is happening is the direction of the vector and the magnitude of the vector will be disturbed. It is no longer the original one. Now this is the point to be noted. Such conditions are known as boundary condition. So now I will write down the terminology. Boundary condition. Boundary condition to be satisfied. Okay. So this has to be satisfied only according to the differential equation that you have, namely the Maxwell equation. Naturally, it is obeying certain rule, and then according to that rule only, this is going to bend like this and go. How it is going to bend, that we will see when we are going to discuss the actual topic. I want to emphasize now the terminology boundary condition to be satisfied. This is not the same as boundary value problem. So that is what I am trying to explain. Boundary value problem means solving a differential equation subject to suitable boundary condition. That is completely different from what boundary condition to be satisfied when the electric field is penetrating into a material medium. Okay. Similarly, what happens is once the material medium is over, now it will come outside. Okay, so once again the same question can be asked. So once the material medium, namely pink color, is over, now no longer pink color is there, which means that the outside you have a vacuum. Then once again you will be having the vector in a different direction, which is parallel to this white color one. So you are now able to see that there is a change in the direction and change in the magnitude because of the dielectric medium, or in general material medium. So such conditions is what is known as the boundary condition to be satisfied, and it is different from solving a differential equation which is known as the boundary value problem. So that is the distinction I would like to mention. So let us go back to our original screen that I am writing there. So this is what I am trying to say. So boundary value problem is not the same as boundary condition to be satisfied by the electric and magnetic field. Okay. So once that is clear, now we will be studying the static cases. So you can now see that all the cases that I have been discussing till now corresponding to the static case. Static case means time derivatives are absent in the equation, because that is the simplest situation. So once you study all these things, and now you will be ready to move next to topic, namely what will happen if you include the time derivative also. So I'll write down that this is the second part of our we can say that like this you can study. Once that part is over, you are now ready to study the dynamic part, namely when you include the time derivatives. So once you finish the static case, now we are ready to study the time varying electric and magnetic fields. So under this particular heading, what is that you are going to study mainly is, let me therefore write down that the main topic is the electromagnetic wave propagation. I'll write down that. And once again, electromagnetic wave propagation we will be doing first in vacuum only. Okay. First we will finish in vacuum. Then afterwards we will study the same electromagnetic wave propagation in material medium. That's what we will study. By that material medium, you can understand that it can be an electrical conductor, or it can be an insulator. That means dielectric. It can be anything. In both the cases, we can study the electromagnetic wave propagation. So that will be your main topic in second part. Once you complete that also, then we will be dealing with a more theoretical foundation on electrodynamics, namely relativity. So that's what I'll write down. The last part of the electrodynamics would be the covariant formulation of electrodynamics. Covariant formulation of electrodynamics. Under that, the first topic, okay, I don't want to list everything, but mainly you will be studying about the gauge invariance. Okay, that will be the main topic, gauge invariance, which means that we will be studying the how the relativity and electromagnetism are connected. I'll write down relativity and electromagnetism. What is the connection between relativity and electromagnetism? So that is what we are going to study. And in particular, let me write down, we will be discussing on Lorentz scalars. Okay, so let me write down that we ask the question, what are the Lorentz scalars in electromagnetism? So that would be the question that we will be answering. So which means that typically if you study all these things, and we say that a second course on electromagnetism will be completed. So now you understand that this particular study will not be overlapping with your BSc level course. So you understand what we are studying and where to start with. I already told you where to start with. Maxwell equation is the starting point. Okay, you don't have to worry about derivation, but you should know that there is something called Maxwell equation. Okay, that's fine. Now let me write down what books we are going to follow. Most of the books are quite familiar and also standard books. So first one, I will write down the Griffiths book. So Griffiths book on electrodynamics. So here I would like to mention a particular point, then I will write down the second book B here. But before writing that, I would like to mention about the Griffith book. Many of you might have already seen the Griffith books at undergraduate, namely in the BSc. But the point to be noted is that the material covered in the Griffiths book is sufficient to study more than 2 semesters, or at least 2 semesters. So which means that an introductory level or introductory part of the Griffiths book might have been studied in your BSc. So that is not a problem. You are supposed to study. Okay, whichever is easy part or whichever is introductory part, that you must study from the Griffiths book at the BSc level. So therefore, just because I am writing Griffiths book, it doesn't mean that we are going to repeat the same thing. So there is no repetition. And you have the second half of the details, namely boundary value problems, boundary condition to be satisfied, gauge invariance, relativistic formulation. All these topics are there in the same Griffiths books, and therefore you can now use this one for the second course. And the advantage is that this is a book which is written at a comfortable mathematical level when compared to another standard book, namely the Jackson book. So I'll therefore write down the second book, J.D. Jackson, Classical Electrodynamics. So this particular book, namely the Jackson's book on classical electrodynamics, is a very standard book on electrodynamics, but however it requires a little higher level of mathematical knowledge. So therefore you should read the Jackson book only after finishing the Griffiths book. So this third third edition is SI unit, so I want to mention that. If you have second edition, it will be in Gaussian unit, so that will give you some confusion. So better you try to keep third edition, that will give you the SI unit. And coming to this Griffith's book, fourth edition, it doesn't matter fourth edition, third edition, anything is fine. Okay, so these are the basic books, and in case if you want to solve some problems, you can use I think StudyQ book is good. I'll write down MNO StudyQ. Title of the book will be Elements of Electromagnetics. Yeah. So coming to the clarity, you should have Griffith's book will be the standard book which is comfortable for reading, and at the same time the mathematical ability or mathematical requirement will be on par with the first mathematics course that you have studied. Whereas if you are going to open the Jackson book straight away, then the book assumes a higher level of mathematical difficulty, especially only in 3 dimension. Okay, Jackson book will not solve any 1D problem, 2D problems, etc. So most of the discussion will be on the 3-dimensional problems, and especially spherical polar part and cylindrical polar. So therefore what happens is a good knowledge in 3D mathematics and polar system, such as the spherical harmonics, that is required actually. Otherwise you cannot read what is written in the Jackson book. Therefore I don't recommend that you open this Jackson book straight away. Okay, but at the same time you have to read this Jackson book at the end. That means finish the Griffith's electrodynamics book, understand, and then you can open the Jackson book and then read the 3-dimensional problem. In the Griffith's book you will be able to see 2-dimensional problem. So now you can see how they are connected. Okay, so 2D means a little bit easy, and 3D automatically mathematical difficulty will be increasing. So we will be going step by step. That is always better. So this is the order. And then what is that? The StudyQ book is about understanding some problem solving. So only when you solve some problems containing numbers, okay, numerical values, your understanding will become a little better. Okay, therefore for problem solving, especially, problems are very interesting, and at the same time it is not difficult. Okay, so it is not difficult. Probably I will write down that particular point. So I want to say that the problems are not difficult in the case of StudyQ, which means that at easy level I will write like that. But at the same time, easy level means it doesn't mean you have to neglect. Okay, so that is also not possible. You have to read some problem, otherwise it's not easy to solve it. So okay, so I think that completes my introduction or so overview about the course structure that we are going to deal with. And so what we are planning to do in the immediate class or the next class is that I would like to start a mathematical requirement to obtain this Maxwell equation. That's what I'm trying to show here. So here it is there, right? This one. So suppose if you want to prove this some of these equation, then we need some mathematical tools like vector calculus part and some other part. So that part we will see immediately in the next class, so that we will be ready to see how to start with the proofs of this equation. So it will not take much time. We can quickly finish this, and once we do that, then immediately we will be ready to move on to the solution of the Maxwell equation, namely the boundary value problem. So that is our plan immediately. So let us meet in the next class, okay, with an appropriate mathematical tool that we can proceed with. Okay, so hopefully I will stop here. Okay.